All right, so let's look at another vertical situation. Here we have like a car going through a roller coaster, so a couple hills and dips. We're going to look at this in a very unrealistic way where the speed will be constant as it goes through the entire track. All right, so speed will be constant. So at each of these points, the top, the bottom, and then the top here, is where we're going to examine this force. Each of them have their own radius of curvature. Right, because if we were able to kind of extend the circle, you get the idea, right? All right, so at the top here, what forces do we have acting on the car? So we have gravity going down, and then we have the normal force up. At the bottom of the curve, we have gravity going down, and then we have the normal force up. And when we're at the top, it's the same as the other one. mg down, normal force up. All right, so if you look at the magnitudes of the arrows that I drew, I tried, at least on the first two, you can see that there's purposely one of the arrows is longer than the other. So remember that the object will only accelerate in the direction of the net force. So if the acceleration has to be towards the center of curvature, what direction must the larger force be? Towards the center of curvature. All right, so when you're on top of the hill, the gravitational force has to be greater than the normal force. When you're coming out of a hill, going out of that bottom part here, the normal force has to be greater than the weight. And you can think about this if you've ever had that sensation. When you go over the top of a bump, you kind of get that sinking stomach feeling where like you almost like lift up out of your seat. So what that is the sensation of the seat exerting less force on you than what you normally feel as your weight. And then when you're coming out of a curve, you feel a little bit heavier, like you're getting pressed down into the seat. And that's because the normal force is pushing up on you in order to pull you out of that dip. So from your experience, you should be able to state whether the normal force is less than or greater than the weight. From drawing your diagram and just thinking through that, you should be able to determine whether the normal force is less than or greater than your weight. Okay, so we know that over the top, normal force is less than your weight. Coming out of the bottom, the normal force is greater than your weight. Now, we need to get the equations so that if we needed to solve for the normal force. So, for the first hill, making positive towards the center, we have mg minus the normal force is going to cause the mass to accelerate. Now, since we're talking about constant velocity here, I'm going to substitute in v squared over r. So if we had to solve for the normal force, we would get it's the weight minus this v squared over r. Now in that right-hand side, the r is constant. So what would happen to our sensation if we went over that hill at a faster speed? So if you go faster, that means that value goes up. And then what happens to this entire value? That also goes up. So you would end up subtracting a larger number from your weight, which is your normal sensation, so that as you go faster over the top of the curve, you should feel lighter which is what the normal force is. You feel the normal force. You never feel gravity pulling you down. Let's look at the bottom. Positive towards the center, so we have the normal force minus mg equals mv squared over r. And again, solving for that, we have normal force equals the weight plus mv squared over r. So here it's saying that the normal force is this much more than the weight. Left side, this much less than the weight. So what happens if we go faster through the bottom of the curve? Again, this entire value increases. You will feel a sensation that is greater than your weight. Now, if we are moving at a constant speed, how does this one and this one compare? So what would be the difference? This one has a smaller r, smaller radius. So if we, going from the first situation to the second situation, the first hill to the second hill, the radius decreases. So if the radius, I'm going to go look at the other equation, because this equation right here is the same for both of these hills. All right? So if the radius decreases, what happens to this whole value? Divide by a smaller number and it goes up. So when you subtract a bigger number from the original number, okay, this will go down. So if you go the same speed over both hills, but this one has a smaller radius, you will feel lighter going over the smaller hill, the tighter curve. All right, let's get rid of some of this and look at a different type of situation that you will not see unless it's an actual AP problem, which would be good news and for your web assignment. So if I put a block on top of a sphere and have it start to slide over the surface, at what point, at what angle will the block fall off the surface? So when the block reaches that angle, I don't know what angle it is, I'm just drawing it there, what would the forces be on the block? Of course, we have gravity, and gravity always acts straight down. And since it's interacting with the surface, it has a normal force, and that normal force will be perpendicular to the surface, perpendicular to the tangent line. First thing is, what would be the value of the force that's acting towards the center of that circle? So if we break this apart into an x and y axis, and we need to find the component pointing here, then we have to know that the angle in between here and here are the same. So that's theta. Okay, two parallel lines. Those two angles have to be the same. So that's going to be mg times the cosine, since the adjacent, the cosine of theta. And that's going to be the force pointing towards the center. We do have a force pointing away, which is the normal force, causing that mass to accelerate. So the problem that I've seen like this is asking for at what angle the block falls off the surface. However, it also uses energy in the problem. So we're not gonna be able to get to the final solution here since we haven't gotten to the energy chapter yet. However, let's just talk about what it means whenever the object leaves the surface. So as the block falls over that curve, something has to change. All right, well, first, the angle's changing so that the amount of force towards the center is going to change, which is also going to cause the normal force to change in the same manner. So if the block reaches a further angle, we have a smaller component pointing towards the center, so that this is going to decrease. And if it's still turning so that it's moving along that circular path, then the normal force has to decrease as well. But once it gets to a point where the normal force equals 0, right, that's when it leaves the surface. We can think about it as a ramp too. So if we had a car going over the top of a surface, the faster that we would go as v increases, and we had that equation here as mg minus the normal force equals mv squared over r. All right, the faster we go, the greater this becomes, and the normal force can end up decreasing to 0. So if this keeps increasing to the value of gravity, then we end up with a normal force that equals 0. So it's basically a ramp. Car can go fast enough to jump off the top. That's what's happening here. So we'd end up with just this part of the equation for the block sliding over the curve and leaving that sphere, and something similar here, except we just won't have that cosine because we're not looking at a point that's off of the top or bottom, okay? So when does the object leave the surface? When it's going over the top of a hill, it's when the normal force equals 0, so that gravity is the only thing causing the car to accelerate. Basically, it's in free fall. It's just flying over the curve. Last year we looked at situations like this, and definitely not like this, for what is the max speed for a car going over a hill, and we can also look at it for the minimum speed for a roller coaster going through a loop. Once the roller coaster gets up here, what's the slowest it can go in order for it to make it around that loop? Well, if we don't go fast enough, the roller coaster is going to go up and either roll back. Go up a little faster, it's going to go up, it's going to hit here, similar to that block sliding over the top. If we're underneath, it can just fall off right here. It can leave the track too soon. We want it to at least make it up to that very top before it starts to leave the track. However, if it has the correct amount of velocity going this way, it'll basically fall along the track and then make contact again and continue through. So that's the minimum speed. So what is the minimum speed needed to make it around the curve? What would be the forces acting at the top? Well, we have, of course, the weight, and if we're going fast enough, we also have the normal force going down. So our equation would be mg plus the normal force is equal to mv squared over r. And when the object leaves the surface, so if we keep speeding up, if we go faster through this loop, this can't change, but you need more force going down to match up with this speed. So if we go fast enough, we're going to increase that normal force. If we slow down, that normal force is going to decrease, and it will decrease all the way to 0. So when that's 0, we get the minimum speed. So you can see the mass now cancels. We have v is equal to the square root of g for the minimum speed. Now, if we looked at the last equation that was going over, is it going to jump off there? Again, when the normal force is equal to 0, you go fast enough, that's going to have to decrease. If we go slow to the point where it just stops at the top, then the normal force equals mg, which would be the max. So we go faster, the normal force decreases. We end up with just one force causing the mass to accelerate, and you get the same exact equation, which is the square root of g. It just depends on, I guess, what side of the curve the object's on. If you're on top of the curve, it'll be the maximum speed. If you're underneath the curve, it'll be the minimum speed in order to continue to make the curve. I think there's only one more type of problem, and that is when an object is tethered to a string, but it's flying around in a circle. All right. And so it's making a cone shape. So when that happens, the object stays along a horizontal plane. However, the acceleration is directly towards the center of that horizontal circle. The forces are going to be the tension and mg. So we can see what is causing the centripetal force. What's the only force listed there that has a component pointing to the center? It'll be the x component of the tension. And we'll have to have some type of angle there. So the circular motion will have an equation for the centripetal direction, and we would also have a sum of all forces in the y for this. And the y component of the tension, if it's going to stay along that level plane, the y has to equal the mg, and that's all you're going to get for this equation. But then the x component of the tension is going to be the centripetal force. Okay. Not too bad of a type of problem, but if we come across it, that's the way we have to look at it. All right, so I think this video is long enough. You want to have fun, go ahead and play it back and count how many times I said so. All right.